Alright, another pulse motor. We're building a different coil, and for the core material we're using this laminated transformer core. That piece is a little bit larger than that, of course, but the same material. So I've done 3 layers of windings already, and you can see I've inserted a temperature probe and put a good dollop of heatsink paste over the top of the end of the probe so as it can absorb all the heat from the windings around it. And we're just going to check out what happens with our coil temperature when we're running it as a pulse motor with our rotor, and then under the same pulse conditions driven by the signal generator without the rotor, and see what happens to the temperature, to give us some indication if we're losing a lot to waste heat with or without the rotor. So just a bit more experimenting on the pulse motor and getting down to the nitty gritty things, and seeing where this power differential with and without the rotor is actually going, or how it's actually forming with the rotor, and how that rotor is reducing our power input but keeping the power output steady. Anyway, I'll keep on winding, and we'll come back when the pulse motor is up and running, but I just wanted to put this on here so you knew what was actually inside this coil and what we're doing and where the temperature probe was placed. So the temperature probe will be about in the middle of the thickness of the windings, so it should give us a fairly good indication as to what the temperature of our coil is doing. Alright, so we'll see you at the finish line. Alright, a couple of interesting discoveries. Yes, we're up and running. Just your standard SSG circuit. I'm going to change this battery out for a large cap with a resistor across it, so we don't get voltage changes during the test. This is just to fire it up, make sure everything's going to work. Now, temperature gauge in our coil there, it started at 77 degrees Fahrenheit. It's been going for about 10 minutes, gone up to 86, which is showing us we're going to get a fairly accurate temperature reading. Okay, the odd things I found. First of all, the tip 3055 transistor. Who knows what base voltage you need to switch them on nice and clean and hard. Well, it seems in the situation of a pulse motor, our yellow trace is showing us the waveform across the base and the voltage that base is triggering on, and the blue, of course, is our current across our input. So if you have a look there, 780 millivolts max, a nice square wave on our base, but only 780 millivolts to switch it on nice and hard for some reason. Alright, at the moment there's 256 milliamps at 12.41 volts. Our output is 116.7 milliamps at 13.95 volts, roughly somewhere near 50% efficient, which is not too bad for a pulse motor. Okay, so that was the first thing I found to be a bit odd, is only 780 millivolts to switch that transistor on nice and hard with the rotor in position, but without the rotor in position, as you would have seen on my other videos, I had to have my signal generator set at around 4 volts to pull that transistor on hard enough. Interesting. Alright, so the other thing that just occurred to me I was doing in my other videos, you'll see here across our input resistor I have the two grounds of the scope after the resistor and the probe before going to the negative terminal of the battery to measure our current. And the reason I did it this way is so I can have a look across the base and in the last videos the collector. What I also had happening at that time was the power supply was keeping our run battery topped up. Now the scope and the power supply, as far as I was aware, share common ground, and that would have meant that as soon as I hooked the power supply up to the negative side, this side of the resistor would have become common ground, and we have our common ground of our scope on the other side, which means we would not have been reading anything across that resistor apparently, but we were. So I just was double checking this. You can see here we have 256 milliamps or millivolts across our 1 ohm CVR, and at the moment I have the ground of my power supply hooked to the negative of the battery, which is this side of our CVR, and the grounds of the scope on the other side of the CVR, which should have eliminated the CVR altogether, but it hasn't. And in fact, I'll disconnect the ground and I'll disconnect the positive. That was actually my digital multimeter reading the voltage that lead. So the power supply is disconnected and turned off altogether, and our current that we are reading, or the voltage across our 1 ohm CVR, has not changed. So this is telling me that the scope and my power supply do not share common ground, because it makes no difference whether I have my power supply topping up the battery and the ground hooked to this side, or if it is not there at all. So that's probably a good thing for us now that I know that the scope and the power supply do not share common ground. Why, I don't know. So I'm not sure if this what's supposed to be the ground side of the scope is actually hooked to the ground side, because I know this common here, between common and ground there is no potential, because they're eventually hooked up together in the meter box. So maybe I do have a floating ground on this scope, because hooking the ground up to this side of my current viewing resistor with my power supply makes no difference to the voltage being read across that power supply. So once again, I'll just take that and hook it onto the battery like so, and you can see that the voltage across that 1 ohm CVR remains the same. So there is no common ground between the scope and the power supply. So that's a good thing. Alright, so what I'm going to do is stop this now, and we're going to let the coil cool down. We're going to give it a 20-minute run at a constant voltage, and like I said, I'll change that for a cap with a resistor and burn off the power that's coming out of the pulse motor, so as it remains the same. And we'll give it a 20-minute run, see what kind of a temperature gain we get. Looks like it's going to set at 87 in this case, and then we're going to stop the rotor, and we're going to feed this signal, what we're seeing here, and because it's nice and square we'll be able to do it relatively easy. I mean, duty cycle looks about 50%, and we're going to feed our transistor that signal, the very same signal that the pulse motor is feeding the base of the transistor, and we're going to do that with our signal generator, so as we can remove the rotor, and then we're going to do another temperature run and see what that temperature says without the rotor in play under the same pulsing conditions. Alright, so I'll log off here, stop the whole thing, which is just of course a matter of stopping the rotor, and everything's kaput. And I'll let this coil cool down to room temperature. I'll make sure the room temperature stays pretty much the same, which it will this time of the year for the rest of the Arvo till it gets relatively late. And then we'll do our temperature runs and see what power we're putting out with the rotor, or what power we're consuming with the rotor, and then we'll do the same without the rotor. See what power we're putting out, what power we're consuming, and see if we get a temperature rise much the same over the same time. Right, so we'll be back when that's all ready to do. Alright, well that has been sitting on 85 for the last half an hour, so I'm guessing it's pretty stable. I don't know why it went up from about 78 to 85 and stopped there, but it's not coming back down any lower than 85. So we've done a bit of our change here. We've put a large cap on here, and across that is a 15.2 ohm resistor, large one. Our battery voltage 12.4849. That will just be that would have just grabbed a bit of surface charge when we've had it disconnected. Drop down fairly rapidly. We'll keep it topped up at 12.42. We've got our book ready to write down our results. Frequency, starting temperature, current. Starting temperature we can write down now. That is 85 degrees Fahrenheit. The resistor we know. Supply voltage we'll write down once we're up and running. The current will do the same, and the frequency we will mark. And the duty cycle, of course, we will need as well. Oh, that was nice spelling. Okay. So yeah, basically we're all ready to go. We're simply going to read the voltage costs at 15.2 ohm resistor, measure our temperature, voltage, current on the input, which is across the CVR, and we will start our little clock here, ready to go. Give it a spin up and get it cranking. I've got the pot turned right up, full 1k plus our 100 ohm resistor there. Volts. Put that down as our starting voltage, 12.46, and I'll see what it is every 5 minutes. It won't drop as fast now because since I've put this cap resistor to burn off our output on, our current draw has also gone down as well. Okay, so 200 millivolts per division on the blue channel, 500 on the yellow channel. The blue channel is our current, the yellow channel is the across the base and the emitter of the transistor. So I am really quite surprised that it's only 760 to 780 millivolts to fire that transistor up nice and hard like that. And the duty cycle I worked out before, it's about 38 to 42%. All we'll be doing is we'll start off with that when we go to drive this with the signal generator without the rotor, and we'll simply bring the output up to the same output, which is 3.7 3.725, 3.724 is quite stable. 3.724 volts over 15.2 ohms. Our input is steady at 12.44 like we have written down. Our current 184 milliamps. So yeah, now with the like point mentioned, now with more waveforms in the screen, the average and mean voltage is the same. So current is 184 milliamps. That'll be the first one. And like I said, we'll do it after 5 minutes again. Our temperature is 87 degrees Fahrenheit now. She's running quite smooth. Alright, so I'll see you in 20 minutes and we'll have a look, see what happened, and we'll let that cool back down to its 85 degrees. It's at 88 now, and then we'll do it all again. We'll disconnect our trigger coil. That's pretty much all we'll have to disconnect, and just hook our signal generator across the emitter and the base. I really can't see it switching on properly at 760 millivolts on the base, so I'll have to see what's going on there. Alright, so we'll be back in 20 minutes. Alright, so our 20 minutes is nearly up. One thing I didn't take into account, you can see a bit of paper blowing around there. That's the windage off of the rotor, which is actually going straight through that tunnel there and across the other side, and that would be keeping the coil a little bit cooler than normal, so didn't take that into account. Anyway, so that's our 20-minute run done, and we're at 12.43 volts, and we're still at 184 milliamps, very stable. And I've just made a bit more of a neater bloody system here. Yeah, temperature is still 91 degrees Fahrenheit. So that looks to be about max temperature we're going to gain. So the dissipation rate has been reached, I would say. The surroundings being able to cool that coil, including the air that's zipping past it from the rotor. Our output is much the same. 3.7 volts over 100 ohms. 15.2 ohms. Late night last night. Nothing like Christmas, and lots of grandkids running around first thing in the morning screaming and yelling. Alright, so and our frequency is 110.567 Hertz. I'll actually where do I put that down? Somewhere here. 110. Dropped to 109.87, so 110, that'll do. That's going to be extremely close. Alright, so now we have to let our coil cool down back to our 85 degrees Fahrenheit, and while it's doing that I'll change everything over, get our signal generator ready to fire up the system without the rotor. All things being equal, our output should be the same, when we get our input the same. If not, we then have to see, well, we're going to do that anyway, see what happens as far as our temperature goes. So it's just clicking up to 92 now. So, 22 minutes, 23 minutes to get to 92 degrees. So I'll just make a little note of that. 92 degrees Fahrenheit at 23 minutes. Just use that as another marker. Yeah, so I'll go ahead, get all this swapped over, let the coil cool down, we'll start it all over again, see what happens with the coil running in the same condition without the rotor in place. Back soon. Alright, so we're ready for our solid state part of the test. The coil is back down to 85 degrees, which was our starting temperature. Recovery voltage on our battery 12.51, which I will have to hook up right now to keep it stable throughout the test. Okay, so our trigger coil is disconnected. Our anti-oscillating diode is disconnected, our 100 ohm resistor is disconnected, the signal generator is connected to the base and the emitter, exactly the same as before. So we're going to run the test the same as we did before. I've got everything very close to being exactly the same as it was before. Frequency, duty cycle, so as we're drawing the same current, and we've also got the same voltage going to the base. Surprisingly, it is actually around 760 millivolts that is required by the transistor to switch it on nice and cleanly. Alright, so all we have to do is turn our function generator on, and we're off and running. We'll also start our stop clock as we did before. And as you can see, I've even managed to get the up ramp on the base the same. So 760 millivolts there, as we had before. 184 milliamps, the exact current we were drawing before. So we're pretty much, well, exactly as we were before. So it started 12.46 volts before, 12.48. That will go down relatively quick, as you can see. And all we have to do is do what we did before and take our measurements every 5 minutes. Now, so our current at the moment is exactly as it was before. Our wave shape on our base is exactly as it was before. 760 to 780, or 184, which is our current across our CBR, and the 760 to 780 was the average forward voltage to our base on our transistor. The difference being so far, even though the power input, which is now 12.46 volts at our 184 milliamps, our output is lower, so which would indicate that some of it has to be being converted to heat. So we'll have to see about that with our time trial and see how we go. So we're just going to do our 20 minutes again. If the temperature rise turns out to be exactly the same, we will then know that without the rotor it's not a case of dissipating extra heat as being the reason that our output has dropped down. So we're just eliminating one thing after another, and I guess we'll see how we go. So we'll see you in the 20-minute run, and see how we go. see if there is extra heat being dissipated by the coil. This would mean a drop in output. Let's see what happens. 3.468 volts over our 15.2 ohms, and before we had 3.71 volts over 15.2 ohms on average. So we'll see how we go. Back in 20 minutes. Okay, so we've just done our 15 minutes, and we're going to write down some results here. First one, you'll notice 15 minutes with the rotor, we're at 89 degrees Fahrenheit. Right now we're at 94 degrees Fahrenheit on the coil. We're dead stable at 184 milliamps at 12.4443. We're at 12.43 volts before, so very much the same. So it's probably going to be about 12.39 or something like that, maybe even 3.1 to show you 12.34 or 44. Our output is 3.464 over our 15.2 ohms. Okay, so that's our 15-minute mark. So you can see here at 5 and 10 minutes we're pretty much in line with temperature, and output was a bit lower without the rotor. But when we hit the 15-minute mark, it was 91 degrees with the rotor and 94 degrees Fahrenheit without the rotor. So more heat being produced by the coil with the same P in, and less output at the moment. So we've got another 3 minutes to go. We'll see how we look. It's ticking up to 95. The maximum temperature before was 92, and that was at 23 minutes. So we've already killed that. So yeah, the coil is hotter. We don't have the small amount of air that was flowing past the coil. I don't think it would make that much difference because it was only very slight breeze coming off the rotor. But may have contributed slightly. I'm not sure. I don't think so. Not that much. Definitely not that much difference. So yeah, everything is the same except for the output and the heat on a coil. Producing more heat, producing less output. So I would say at the moment the output here that has gone down is being lost to heat in the coil because our input power is exactly the same. Alright, we'll see you in a couple of minutes. Okay, final few seconds, and there's our 20-minute mark. We have 96 degrees. There's our final temperature. We still have our 184 milliamps at 12.34 volts, which was exactly the same as our last test with the rotor. Our output is 3.463 volts over our 15.2 ohms. So there you go. Without the rotor, less output power, more heat generated by the coil. So it means one or two things. The wind, or the airflow across the coil from the rotor, was enough to keep the temperature down to what it really should have been. And we can actually test this simply by putting a bit of timber or something between the rotor and the coil so the air doesn't flow past the coil. Well, the other thing it means is that with our spinning magnetic field, alternating magnetic field going past the coil, it changes the coil so as the coil produces more output power than and less heat. So there you go. Alternating magnetic fields are what is converting heat in that coil into an electrical output. Doesn't matter how it's doing it, it is doing it. Just let it go to our 23-minute mark, see what the temperature is. So yeah, that's about as close as we can get to simulating our pulse motor, and you must agree that is extremely close, right up until the small ramp up that we've seen on the base before with the pulse motor. The current trace has a slightly flatter top. Other than that, that coil is being driven pretty much well identically to what it was with that rotor. So managed to hit 97 degrees at the 20-minute mark without the rotor, 23-minute mark, and it was 92 before, so it's a difference of 5 degrees Fahrenheit. And I don't think the wind blowing past that coil from the rotor would have done that, but like I said, we can test that if need be. So without the rotor we should produce more heat, less output power. With the rotor we produce more output power, less heat. The only thing that rotor has is alternating magnetic fields spinning past the coil, which means ultimately that it is managing to convert heat energy into electrical energy, regardless of how it's doing it, what it alters in the coil. It is those magnetic fields that are doing it. Alright, so that's us for this test. I'll put all this mess together and stick it up on the thread, and we can have a little discussion about that, I guess. Thanks for watching.